The other piece that has to come into acid-base chemistry is the idea of the common ion effect. And we've already talked about this in terms of solubility. We know that in solubility, if there is already a common ion in the solution, that solubility decreases. Well, common ions also have an effect on acid-base chemistry. A set of notes for this is available for you in Schoology. So, again, the common ion effect is the effect on a solution chemistry when we have a solution or an acid base that is being added to a solution that already has an ion in common with the solution being added. Okay, plays a part in acid-base chemistry, which is what we're talking about now. It also played that part in solubility or precipitation chemistry, which we talked about earlier. All right, so when we have a common ion, what happens is we change the equilibrium. So this is only going to be something that affects weak acids and weak bases. Okay, so in the equilibrium of a weak acid, if we have a common ion, it's going to decrease ionization. Okay, so if we're talking about a weak acid, that means we're going to be making less H+, and so that means that the pH is going to be higher. It's going to be not as acidic as we would have expected. So the higher concentration of a common ion that we have, the less ionization there is. The lower the concentration of the common ion, the more ionization that we have. If there is no common ion, then it will ionize fully to its Ka potential. Okay. This again, just like our other common ion situations, is part of or is being governed by Le Chatelier's principle, right? So for example, if I had this acid-base equilibrium set up, and this is the acetate ion, and I put extra acetate into the solution, then what would happen is we would have an increase in the common ion. That would cause a shift in the reaction to the left, which would decrease the amount of H3O and increase the amount of undissociated acid in the solution. So as a result of that, we go more of that common ion shifts it left, more reactants is produced, which means we have less ionization, less H+, and again, less H+ means that the pH is going to increase. All right, so how do we calculate pH with the common ion? Well, we're going to rice it. We're going to make our regular assumptions regarding low ionization to simplify things, and we'll check our assumptions for that, and then we'll figure out the log of H+ with that. Okay, so as we're ricing it, we just need to be aware that our initial concentrations will also include the initial concentration of the common ion. So here's an example. What is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution? Ka equals 1.8 times 10 to the negative fifth for acetic acid. All right, so we're going to go ahead, and we know that our reaction, our acid-base reaction here, is going to be acetic acid, which we'll abbreviate as HAC, going to H+ or H3O+ if you want to do that, plus AC minus. Okay, it's the acetate ion. All right, so pH of the solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. Okay, so my initial concentration of my acetic acid is going to be 0.3 moles divided by 1 liter, so that's 0.3 molar. Okay, my AH+ concentration to begin with is going to be 0, and my acetate concentration to begin with is also going to be 0.3 molar, 0.3 moles divided by 1 liter. All right, so now based on my stoichiometry, this is going to be minus X plus X plus X, and that gives me a change of 0.3 molar minus X, X, and 0.3 molar plus X. Okay. So now at this point, we go ahead and we look and we say these are in the order of 10 to the negative first. The Ka is in the order of 10 to the negative fifth. So the equilibrium is not going to change the concentrations of those two very much at all. And so as a result of that, we can go with a concentration of equilibrium concentration of 0.3 molar there and 0.3 molar there. All right, so then we got to figure out the concentration of H plus then. Okay, and we do that using our Ka. So Ka is going to be H plus AC minus over HAC, okay, which if we expand that out, that is 1.8 times 10 to the negative fifth, which is equal to X times 0.3 molar. That's 0.3 molar as well. Okay, those are going to cancel out. So therefore, 1.8 times 10 to the negative fifth is going to be our concentration of H plus. So then finally, pH equals negative log concentration of H plus, which equals negative log 1.8 times 10 to the negative fifth molar, okay, which equals 4.74. Okay. Now, in an earlier practice problem that we did in this unit, we did the exact same thing of a solution of acetic acid that was 0.3 molar, but didn't have the common ion. And for that one, we found a pH of 2.64. So you can see that the addition of the common ion dramatically increased the pH and lowered the ionization of our solution, of our acid in this particular solution. All right, last thing we would want to do here is we would just want to double check to make sure that our percent ionization is less than 5%. And you can probably tell just by looking. We've got 10 to the negative fifth here and 10 to the negative first there. And that is certainly going to be less than 5% ionization. All right, let's do one more. Calculate the fluoride ion concentration and pH of a solution that is 0.20 molar in HF and 0.10 molar in HCl. Ka equals 6.8 times 10 to the negative fourth. All right, so let's start off with this. So we're going to go rice. Okay. And my reaction in this particular case is HF goes to H plus F minus. All right, initial concentrations. The concentration of HF is 0.20 molar. Okay. The concentration of H plus in the solution is coming from this strong acid right here, which would be 0.10 molar. And the F concentration to begin with is 0. Okay. All right, so then, according to stoichiometry, we have minus x plus x plus x. We get 0.20 molar minus x, 0.10 molar plus x, and x. And again, looking at a Ka of 10 to the negative fourth, we will say that that is significantly less than 10 to the negative first and 10 to the negative first down here. So we're going to assume that these are 0.20 molar and 0.10 molar for right now. All right, so then let's go ahead and set up our Ka. So Ka is going to equal the concentration of H plus times F minus all over HF. So translating that out gives us 6.8 times 10 to the negative fourth equals 0.10 molar times x all over 0.20 molar. Okay. And if that's the case, then we can solve that for x, and we will see that x equals 1.4 times 10 to the negative third molar. Okay, so there's our first question. There's the answer of our first question is that fluoride ion concentration is 1.4 times 10 to the negative third molar. Okay, so then the next thing it asks us is what is the pH of this particular thing. Okay, so pH then gives me is the negative log of H plus. Okay, we can then go ahead and calculate that out, which gives me negative log 1.4 times 10 to the negative third, which gives me 2.85 as a pH. Okay, last thing we probably want to do is we just want to make sure that our assumption was valid. So if I look at 1.4 times 10 to the negative third as my ion, or as my concentration of F, the original concentration of HF was 0.2 or 0.1. So 1.4 times 10 to the negative third divided by 0.2 gives me way less than 5%, and so our assumption is valid. And that's what we need to know about common ions and acid-base chemistry.